now we have the last hour on analytic manifolds, and later on this afternoon we'll see that we'll discuss algebraic geometry of such fields to consider, and we'll see that the k-points of those are analytic manifolds, essentially. So this is why we developed their theory. So now discuss the notion of immersion. So the following are equivalent. If phi of x is injective, so I remind you, this is an operator, a linear operator from the tangent space to little x to the tangent space of phi of x. So so this guy is injective. And now write the bunch of equivalent condition for that. This is basically the definition of, well, maybe I'll so basically what I'm defining here is an immersion at x. So there exist of the neighborhoods u of x, v of y, which is phi of x, and w of 0 in and maybe let's fix the rotation. By the way, I never said it, but it is clear how to define the notion of dimension at a point. Basically, when you have an analytic manifold, the dimension is a locally constant function. Obviously, we assume that the dimension is equal everywhere most of the times. It's constant everywhere. So we have neighborhoods of x at x, of y at y, and of 0 at some linear space of the complementary dimension. such that, or maybe, and we have also analytic isomorphism. So isomorphism in the category of analytic manifolds. This is the obvious isomorphism, and this is the obvious injection, and this diagram prints. So this is 2. 3. While I'm writing, you should figure that 2 follows from 3. Or maybe I should explain what I mean before you figure that. 3 looks like 3 should follow from 2. Sorry. A linear injection at x. I'm explaining what. No, looks like linear. Looks like whatever at x means the following. I'm having maybe x goes to y here. I'm having kn injects. This is the linear injection. And to say that this guy looks like this guy is to say that I'm having some u here, v there, and this is the restriction map, and I'm having maybe u prime here, v prime here. This is the restriction map, and the statement is okay. You have isomorphism making this diagram complete. So this is this diagram, basically by having whatever map here, is saying that this map looks like that map locally at x. X is, and there are words missing. U and V are open neighborhoods, blah blah blah. And it's very easy, and you should figure out now, while I'm writing the next thing, that 3 follows from 2. This is just an expression of what I said by means of coordinates. Coordinates. Fi at x. Gj y. That Fi. Again, 3 implies 4. This is easy, this is just a formulation. 5. this sigma here in these linear coordinates is just the projection from Km to Kn. I mean, the projection of a vector on the first n coordinates, basically. So again, 4 or 3 times 5 is equal. So of course, all these statements are not part of the theorem. And also I claim that 5 implies 1. Okay, this is then the theorem. This is easy as well. If you have this, then you must have injectivity, and the only non-trivial part that should be explained, but it is easy for us because we know this one, is 1 implies 2. So for that, since everything here, actually all the statements are local, so I can replace x and y at neighborhood system at x and at little x and little y. So just write it down. Y is open in Kn. Actually, I'm just embedding Y in Kn. So the image of little x is 0, I'm assuming. And up to choice of coordinate, or maybe, yeah, I'll assume that the image of dpx is Kn. Okay, so the standard Kn in Kn. Take W, maybe it's not my final W, so this will be my W prime. So I want this. This would be the linear complement of Kn, and I'm defining now phi prime from x cross W to y, but this will be given by taking x, comma W to phi of x plus W. Now, check that dphi prime x0 is invertible. Actually, what is easy to check, this is injective. Right? I mean, what is... Yeah. dphi was injective, so this dphi prime is injective as well, but now it's from an n space to an n space. So this means that it is actually invertible. So, you obtain by the inverse function theorem, so phi prime is a local isomorphism. exists u times w inside x times w prime. This is a neighborhood of x times 0. Neighborhood. And v in y is a neighborhood of 0, which is 1. Well, such that so what is this? See? Just to check if you follow. So this is field grinding for the more pedantic form. And we got to, right? So we see all the circle of implications. So we see that all these equivalence conditions, all these conditions are equivalent. And as I said, by this we define a local immersion, or an immersion at a point. We think of it as X being a submanifold of Y. And now I'm erasing the theorem with information. I'm making a global definition. Is an immersion. Is an immersion at any point, or at every point. And phi is an embedding. It is an immersion, and it is an owner on its own. Okay, the next thing I want to do quickly is to give you a dual definition of submersion. With information, I will not prove anything. I write it as fast as I can on the board, and we'll go on. So again, I'm writing the equivalence condition of phi being a submersion at the point. Now I think that, now m is bigger than n, right? So W is a complementary guy to Y, but I need locally to take the product of Y and W in order to get X. The diagram here. Great. This is projection. 3. Phi looks like a linear projection. At X. And we know how to draw the diagram that defines that. Follow same ecoordinates. Such that now I'm writing the projection, this linear projection, but in X and Y themselves, locally. So this is sigma. Oh, sorry, sigma is a section of this projection. So I leave it to you to verify this. No. Just I'll write down the obvious definition that I want to make. If the conditions hold, we say
the other verb
I mean the obvious one,
correct.
which is 1 of 2.
Yeah.
And I doesn't really begin. Submersion. What they say earlier. So I think this is a Burkean notation, like a pan. Immersion is actually a word in English, and submersion is something you take im and make it into sub. Get it or not. At least this is my understanding. We say that phi is a submersion if it is a submersion Okay. Next and last thing I want to say, again on manifold, is kind of on the same. Also, those things again are not the definition themselves, but the fact that they are all equivalent, all the conditions are results of the inverse function theorem. And lastly, I want to come up with a criterion for understanding where is a submanifold of a given manifold actually a submanifold. So I want condition on a subset of a manifold to be a manifold itself. And of course, this is a local thing, so I'll write it down in coordinates. I'll start by basically this is part of the theorem that I'm about to write down, but this is a pre-discussion. So I'm having analytic functions on x. That's function n. Now it's less than n. If you want this analytic map to KR, and I want to look at the zero set of this map, and to say that under generic conditions, the zero set of such a map is a manifold itself, n minus r dimensional manifold. This is what I'm about to say. So here's the definition. X is regular if the rank of that matrix is R. Since rank I can define by non-vanishing of a certain determinant, or a determinant of a certain minor, this n times R matrix, I'll get the following. Is it clear? So now I'm looking at, again, the zero locus of the function f. F, of course, is a function given by the tuple fi. And I'm assuming I'm in U. So let's call it y. Assume we have something like that. So here's the theorem. we may assume X is in Kn open and Y is like taking a neighborhood system and Fi analytic point in the neighborhood. We also assume again by changing coordinates. This will be a certain subspace of Kn. And by changing coordinate, I can assume it to be whatever subspace of that dimension. What is the dimension of this? So let's write n. And these are the standard vectors, the EIs. And now, so as we proved the last one theorem that we proved, what we had is something which was not a local isomorphism. I had something which is left. It was surjection, local surjection or local injection, and I kind of completed it into a local invertebrate thing, and this is what I'm doing now. So I'll consider a new function and from X, which is a subset of Kn, to Kn itself, and it will be the following. I will just take the coordinate functions to be my first n, and then I'll take the last fx. Obviously, it is analytic. And again, if we have 0, you can see that it is injective, right? What is the kernel of it? The kernel of it must contain in the kernel of the f's, it must contain in that thing, but I'm injective of that thing too. So again, injective, hence inverted. It's probably one of the most difficult, most deep terms in math. That the linear transformation from an n space to an n space which is injective is actually inverted. So phi is invertible from corresponding neighborhoods with u. And this is this neighborhood in K. So now it's clear. Phi minus 1 is a local neighborhood 0. And phi minus 1 restricted to that linear space. Is a locus. By restricting phi inverse to that linear subspace, I'm getting a good definition of charts in Y. And I guess so this goes from the intersection that space. So this defines a good chart, and of course, to be precise, what I give here is just a sketch. You need to check that everything is compatible. That the way I'm defining charts is compatible. I mean, at various points is compatible, etc., etc., etc. But this is just fun. Any questions so far? Okay, so I want to start a new subject. Ideally, we will take a break now. Do you want to take a break now and to come back like 10 minutes before time? I think this is a natural thing to do. Now it's 1:10 approximately. So let's take a break. Let's come back not at 2:30 but at